Now we're going to start applying these formulas and filling out your notes. So first of all, the formulas we will be using are the circumference, which C equals 2 pi r, or C equals pi times the diameter. We'll also be using the area formula for a regular polygon. Area is 1/2 the apothem times the perimeter. The circle area is pi r squared. Now, some other things that are not on your math chart, which might be helpful, is the arc length. The arc length is basically whatever portion of the circle the distance around is being made. So when you have an arc, you're going to say how many degrees it takes. And you're going to take that over 360. So if it's a 180-degree arc, it's going to go halfway around the circle. It'll be half of the circumference. If it's a 90-degree arc, that'll be a quarter of the circle, because 90 over 360 is 1/4. So you just take that fraction and you multiply that times circumference, 2 pi r, to get the arc length. Sector area is very much the same idea. You're going to say however many degrees the area of the circle that you have over the total, which would be 360, times the area formula. And we already talked about the central angle. The easy way to find that is to divide 360 by the number of sides of the regular polygon. The steps you want to use to solve the problems: first of all, you want to write down the information from the problem. What kind of shape is it? Do you know the area or the circumference or the arc length? Any of these could show up as known values, and also any of these could be the unknown value. And go ahead and you put a question mark in for the unknown. Now, the apothem, as I said before, A, is the distance from the side to the center of the polygon. It's the altitude of that triangle that you're creating with the central angle. The central angle of a regular polygon has its vertex at the center, and then it connects to 2 consecutive sides. It doesn't skip any vertices on the edge. And the P stands for the perimeter of the polygon. And that it's pretty easy to find. You just take the length of each side times the number of sides, and you'll get the perimeter. So the next step is to write down the formula that you'll need. It could be the area formula or perimeter, or it could be an arc length. And then make sure you use the correct shape on your math chart. And then rewrite the equation that you've set up from the previous step, except now you're putting in the numbers from your problem. So let's go ahead and start some examples. Example 1. The end of the minute hand on the Big Ben clock in London travels 18 feet between 4:05 and 4:15 p.m. By the way, it was actually accurate when I had it at 4:20, but I changed it and I forgot to change the distance. So anyways, this is still pretty close. 18 feet in 10 minutes. How many degrees did the minute hand rotate, and what is the diameter of the clock? So first of all, the degrees in 10 minutes, that's out of 60 minutes total. So the fraction of a full circle is 1/6 of a full circle, or 60 degrees. We know the arc length is 18 feet. Notice how I wrote that down as part of my information, and we're looking for the diameter. So here we can see I use the arc length formula I had just kind of set up in your notes. You just take the fraction of the circumference. In this case, 60 degrees over 360, and multiply it by 2 pi r. Now I don't know the radius, so when I substitute in here, I put 18 equals 1/6 times 2 pi r, and I went ahead and simplified the 2 and the 6. And now I can go ahead and solve that for r. What I did here is I multiplied both sides by 3. 3 times 18 is 54. 54 equals pi times r. If I'm trying to solve for that, I have to divide both sides by divide both sides by pi. And I get a value for r of about 17 feet. That means the diameter of the clock is 34 feet. The next question asks how many pint-sized cans of paint are needed to refurbish the face of the clock if a can of paint covers approximately 48 square feet. So I need to find the area. Now I already know the radius and the diameter, so I'll use the area formula, which is pi r squared. Substituting in 17 for a radius, I get 289 pi, or 908 feet squared. Then I can just take however much the can covers and divide the 908 by that to get the number of cans. I get 18.9, but I really need whole cans, so I'm going to get 19 cans. In the next problem, I'm looking, and these are actual, I looked this up on the internet, these are actual irrigation systems. If you ever go out into the country and you see these huge irrigation systems and they look like they're a mile or two long, those are actually real. They're probably more like a quarter of a mile, a third of a mile long. And this particular one is an average irrigation system. It has a radius of 1,260 feet. The system travels 5 degrees in 30 minutes. So the question is, how many square feet can the irrigation system cover in 4 hours? Well, I went ahead and found out how many degrees it's going to travel in 4 hours. I just went ahead and set up a proportion. I said, well, if 5 degrees is in 30 minutes, then X degrees, what I'm looking for, is in 240 minutes. Notice it's not 4 hours here, but I changed it to minutes. When you solve that, you find out that X is 40 degrees. The other way you could have done this is said, oh, 5 degrees in 30 minutes, 10 degrees in an hour, so 40 degrees. That probably would have been faster. Now I'm going to use the formula for sector area. And the only difference between this and the area of a circle is I have however many degrees out of 360 in front of it. So if I travel 40 degrees over 360, and then I go ahead and put in the area, pi r squared, and I simplified the 40 over 360, that means I travel 1/9 of the circle. Substituting into my calculator, I get a value of 554,176 square feet. So in 4 hours, this system can cover almost over 500,000 square feet. Pretty amazing. In example 3, we want to find the perimeter to the nearest centimeter for this regular hexagon, and the apothem is 8. And we also want to find the area to the nearest square centimeter. So to find the perimeter, it would be helpful if I knew how long each of these sides are. So one thing I'm going to do is find the central angle here. So the central angle is 360, because it's always 360 degrees in the center. And I have 6 of these sides. So I'm going to take 1/6 of that 360, or 60 degrees. Now, when I create that triangle, let me show you what I mean. When I create this triangle here that creates a center angle, I'm cutting this 60 degrees in half. So that means I have 30 degrees right here. And then this other angle here will actually be 60, because this angle right here is always a right angle. The apothem is always a right angle with the side. Now, I don't know if you noticed, but this is a special triangle. It's a 30, 60, 90 triangle. So here's the triangle from our problem with the 8, and I'm looking for this distance over here. And I copy the triangle from the math chart. This is the 30-degree angle, and that's a 60. Well, I go ahead and set up a proportion, 8. So if I cover that, that's this side here and that side there. 8 is to square root of 3, as x is to 1. Cross multiply, and so I get 8 equals square root of 3 times x. Then I have to divide both sides by square root of 3. This simplifies. So I end up with x equals 8 over square root of 3. Now the side really needs to be 2 of these, because when I was looking for x, I was actually looking for just half of that. So I wasn't looking for the whole side, I only looked for half. So the side is 2 times this, or 16 over square root of 3. To find the perimeter, I just have to multiply this by the number of sides. So in this case, it's 6 times s, 6 times 16 over square root of 3, or 96 over square root of 3. I actually didn't find the value to the nearest centimeter. I'll leave you to do that. The area is going to be 1/2 times the apothem times the perimeter. The apothem is 8 centimeters, and here is my perimeter. When I go ahead and substitute this in the calculator, I get 166 centimeters squared. For our last example, we're looking at a stop sign, which is a regular octagon. And there are two of them. There's a 30-inch stop sign and a 36-inch stop sign. The question asked for the percent increase in metal needed to make a 36-inch, the bigger sign, instead of the smaller. So first of all, I need to find my central angle. I divide 360 by 8 because there are 8 sides. I get 45. I only want half of that angle. That's going to help me find this side right here. So I'm doing 22.5. Also, I know the apothem. It's this vertical distance right here is 15. Why is it 15? Because the height is going to be half of this distance. Center's right in the middle, and the height will be halfway across. So I use my trigonometric functions, tangent in this case, because I'm looking for this opposite side, which is x. I know this is 15. Opposite over adjacent is tangent. Tangent of 22.5 equals x over 15. I multiply both sides by 15, and I get a value of 6.21. To find the perimeter, I need this whole side. So I need the whole bottom piece right here. So I have to multiply that by 2. So 2 times 6.21, and then I have 8 pieces, so I multiply by 8. So the 8 comes from 8 pieces. The 2 comes because I only found half, and my perimeter is 99.4 inches. Now to find the area, I use the 1/2 times the apothem times the perimeter. The apothem is 15. The perimeter I just found there, it's 99.4. And when I use my calculator, I get 745 6/10 of an inch squared. Now I'm going to do the same thing for the 36-inch side. So the apothem now will be 18. So that's why I have an 18 on bottom here, whereas I had a 15 on bottom there. The smaller sign had a 15 apothem, the larger sign has an 18 apothem. Where did I get 18? Half of 36 is 18. So opposite over the apothem is tangent, same tangent. And when I go ahead and multiply both sides by 18, I get 7.46. So the perimeter, still 8 sides, and this value is only half, so I have to multiply it by 2. So 2 times 7.46 times the 8 sides, and I get 119 3/36 of an inch. So that really should be inches there. Then to find the area, I go ahead and substitute into the 1/2 AP. A was the apothem. So I have 18 and 119.36. I get 1,074 24 inches squared, or square inches. To get the percent increase, I need to find the difference between the two in area over the original area. And when I say, so I take the larger area minus the smaller area, the starting, all over the original area, which was the smaller one. And when you substitute in that calculator, you will get 44 hundredths or 44%.